So before we talked about intermodulation and the intercept point, specifically the OIP3. But we can generalize the concept of an OIPn where n could be 2, 3, or 4. And what we notice is the slope of the intercept line is simply n over 1. And we can calculate where the intercept is by using the same trick we did before. So give me a certain power level and tell me what the delta P is. So here's the power level, here's the delta P, and then what I'm going to do is divide by n minus 1. And the reason I do that is this goes up by n for every 1 dB P1 goes up, and P1 by definition goes up by 1 dB. So the difference between these two, the change in delta P is going to be n minus 1. And for n equals 3, so OIP3, 3 minus 1 equals 2, and that was the change in delta P. And so that's how we can find out where the OIPn is graphically. And remember that the OIP3 is simply the IIP3 plus the gain. And that's because in a log-log plot, the gain is just an offset. So that's just a reminder. So we're going to talk about how we calculate the intercept of cascaded stages. And you can see already the equation has shown itself down here in the bottom. And what we're going to do is we're going to slide all the intercept points of all the stages to one side of the chain. So we could slide them all to the input or all to the output. And the difference between the input and the output IP3 is just going to be the gain of the system. So it really doesn't matter where we do it. So we can just pick one. And in these examples, we're going to be looking at the OIP3 or the output. And so calculating the total intercept, we're not going to derive it here. I've just given the equation. It's sort of like calculating a parallel resistor. And so what we want to do is we see that 1 over the total is equal to 1 over the last stage, 2, plus 1 over the gain, 2, of the OIP3 of the previous stage. And if I were to go on, I would have 1 over gain, gain, as we did before. We just keep on multiplying the gains like we did for noise figure. And while we're here, let's look at how would we optimize this. So what is an optimal OIP? Well, that would be a very large value. So if this is very large, that means that this is going to be very small. And so I want to try to minimize this right side. And the way to do that is to maximize the two denominators. Now, the only way I can maximize this denominator is to make OIP3 very high. And that translates into this stage being very linear. Over here, I've got a gain term. And so that means if my OIPn for the first stage isn't so great, I compensate for it with the gain. So this gets compensated for that gain. So it's helpful for me to have high gain at my output stage because that'll help reduce the effects of this, and it will also but at the same time, I need to make sure I have high linearity. And the way to think about why high gain helps me out is if I have high gain in this stage, then this can be low gain, and I'm not going to create very much of an intercept because I'm not going to have a large output power. So let's look at a quick example. And we're going to calculate IIP3 for two amplifiers shown below in two different configurations, and we'll contrast the two. So the one on the left, there's two amplifiers, and we've got the gain and the IIP3. But our equation we've been dealing with is in terms of OIP3. And so I'm just going to calculate the OIP3 really quick. And it's easy because it's just the sum of IIP3 plus the gain. And that's because we're looking at a log relationship on a log-log plot. So that's 30 dBm. And over here, OIP3 is just going to be 20 dBm. Now, because we're adding when we calculate our OIP3 total, we need to convert these to linear. And so I'm just going to take this to a different color. And so this is equal to 10, this is equal to 100, and this is equal to 1,000. And it's easy to do because, for instance, OIP3 is 10 to the 30 over 10, and that just equals 1,000. So I can do that in my head really quick. This is going to be 100, this equals 1, and this is going to be 100. So 1 over OIP3 total is going to be 1 over 100, that's the first stage, plus 1 over the gain, which is 100, that's this gain, times the OIP3, which is 1,000. And if you calculate out the math, you end up with OIP3 total is roughly 19 to 20, I think it's 19.6 or 19.7 dBm. And that's the OIP3. And to get back to the IIP3, we just subtract 30 and we get minus 10. If we run through exact same calculations on the bottom, what we find out is we end up with the total IIP3 as being minus 3 dBm. So it's better. And if we look at why it's better, we can notice here that we have a decent gain, but what we've done is we've moved the low IIP3 to the input, and we have the highly linear stage on the output. And as we talked before, that's really going to help us out because this is going to get multiplied by the 10 to make it better, and then this is going to keep that stage linear on the output. And I'll just do the math real quick. So we're going to have 1 over 100, that's coming from this stage, plus 1 over 10, that's the linear version of the gain, times 1 is the, I'm sorry, let me, so let me calculate that really quick. OIP3 is going to be 30, which is 1,000. This OIP3 is going to be equal to 100. And so if I do a quick calculation, I do 1 over 1,000 plus 1 over 10, it's because my gain is equal to 10, times 100. And you can see here that both of these are now equal, and that's why I get a better performance for my total IP3 on the output, because my output is much more linear, and I have this gain to help me with the fact that this is not as linear as I would like. So next comes the question, underneath my writing, of how should you choose your amplifier to prove the linearity of the chain.